where we will be doing the local infra setup for this entire MLOps platform. Before touching any command, I want to clarify why this matters. In real world MLOps, you don't need to run on laptop or notebooks. They run inside container. Those containers are orchestrated by Kubernetes, and some setup must work in development, staging, and production. Kubernetes gives us the consistency. By running Kubernetes locally, we get the production like environment without paying for cloud resources. And whenever we build here, and whatever we are going to build here, will later work the same way. It's guaranteed to work on AWS, GCP, or Azure as well. So now let's break down each component we are installing one by one. So the first thing first, make sure to install the Docker. If you can install Docker Desktop, then that will be best. Docker is the foundation of everything we are going to do. When we run Kubernetes locally, the Kubernetes nodes themselves are created as Docker container. When you hear Kubernetes here, understand that Docker is doing the heavy lifting underneath. This is why Docker must be running like command like kind. So then it's possible. Second thing, for this specifically for the Mac user, they can install something called as Homebrew. It will be very easy for them to add packages. So for example, you can add Docker with the help of Homebrew. You just need to copy this command and come to your terminal and run it. It's that easy. So installing Homebrew is also very easy. You just need to copy this command. Make sure to come this website brew.sh. And Homebrew is simply a package manager for macOS. Instead of manually downloading the binaries and worrying about the version, Homebrew install tools like Kind, kubectl, Helm in a clean and reproducible way. This ensures everyone following this course end up with the same setup. And now let's talk about the core Kubernetes tool that we are going to use. First one is kubectl. So let's search if we have the kubectl. Yeah, so kubectl is a command line interface for Kubernetes. Every time you run command like kubectl gets node, kubectl apply, kubectl log, you're directly talking to Kubernetes API server. Think of kubectl as your remote control of the clusters. And the next tool that we will be installing is Kind, Kind, actually Kind Kubernetes. So Kind is the tool. Kind actually allows us to create fully functional Kubernetes cluster on our local machine. When we run command like kind create cluster, as you can see, it spin ups the Docker container that act as a Kubernetes node. So this is not a mock or simulation. This is real Kubernetes behavior, which is why it is perfect for learning machine learning MLOps correctly. So third tool that we want to install is the Helm. And Helm is the package manager for Kubernetes. In production, you do not manually deploy complex system using raw YAML file. Instead you install applications like MLflow, Airflow, Prometheus, Grafana using Helm chart, and this is what we are actually going to do. So uh, so let's do one thing. Now we have enough overview of this module. This is important module, and I wanted to make sure that every one of us have the right amount of tools ready for us to start doing this project. So first of all, let's first, once you have installed the brew, let's install brew, install kind, and we want kube ctl and then helm. let's let them install. So once the kind is installed, we are going to actually create our cluster, uh, provided there are the configuration is provided. So let's also do one thing, and let's take our first step and define the kind-config file. So meanwhile it is installing, let's define kind-config dot YAML. So here we do this kind. What we are going to do, we are going to make the cluster, and it's a good idea to define the API version. So the one I'm using is kind dot x hyphen k8 k8s dot io slash v1 alpha 4. So this is the version that I am following. And then let's define the nodes. And for defining the nodes, let's also define roles. It is going to work as a control panel, so let's also define p control plane. And then we need to do some port mapping extra. So what I am doing right now here is doing some port mapping, which is mapping the container port. So container port 330,000 to host port 8080. Oops, they need to be same indentation level. Host port protocol, that's pretty much standard stuff. You can type it. We are going to follow TCP, and then we also need to define, let's copy it. And now let's go ahead and the next port, let's define 8081. Let's define their role as worker, and second role as also worker. So just make sure that these things are correct, and once this is done, our kind configuration is defined. Let's create our first kind cluster. So let's type the command CRE8 create cluster name, and we can name as MLOps cluster 1, and we can pretty much create any name here. Then you need to provide the configuration path, the file that we had just created. We can provide that, and now it's going to do, oh, let's actually check if our Docker daemon is running. I believe the Docker container, yeah, Docker is running. So it's saying kind experiment exited, daemon failed to programming external activity on endpoint, control panel already allocated. Okay, all right. So what I understand, maybe the issue is actually we need to, since I'm running everything so previously, so there was some port allocated. Let me shut down. Mm, so now it's going to let me wipe off all of the previous clusters. So this thing can happen. You need to make sure that your so for you it's not going to create an issue. Just a local issue for me. Now it should work fine. And it's starting the control panel, installing storage class, and it's joining the worker node. So we are creating the MLOps hyphen cluster one using this command. So this name is intentional, and what we are doing here is to, like, clearly we are trying to avoid accidental deployment to the wrong environment. And the file kind hyphen config.yaml controls how the cluster is created. So it defines things like number of nodes, number of resource limited. This becomes important later when we deploy heavier services like Airflow, MLflow. And so yeah, after the cluster is created, let's verify everything is working. So let's come here, let's clear, and let's run the command kubectl cluster info hyphen context. We have to provide kind MLOps cluster hyphen one. This is the cluster we have created. So it is Kubernetes told us control panel is running at this port, and core DNS is running at this namespace kubedns DNS proxy, and that's really good. We were able to so what is happening when we run kubectl cluster info? We are checking the kubectl can communicate with Kubernetes control panel that we just created, and now let's run kubectl get nodes here. See, we are now what we are doing, we are confirming that the Kubernetes has active worker nodes in ready state, and let's see, it is in the same naming convention. Now let's quickly recap what setup we what setup that we have done is doing behind the scene. So first we check for the Docker, if whether our Docker is running or not, and then we installed brew. For me it was already installed, and then we installed kind kubectl helm using homebrew. After that we created a cluster name MLOps cluster -1, and then we ran some command cluster info get nodes. So now what we have done is created the clusters, and they are in the healthy state, and they are up, and every experiment tracker pipeline model deployment will run on top of this infrastructure only. So that summarizes the setup module 0, we can say model 0 of this tutorial. And now we can start doing the training cycle of this MLOps pipeline, where we will use MLflow on Kubernetes. At this point where MLOps actually starts to feel real, before we run any command, let's understand why MLflow is so important. In production, machine learning training or machine uh, the let me open MLflow actually. So in production machine learning, a training model once is useless if you cannot reproduce it. You need to know exact what data version, which code, which parameter, which environment produces given model. Without that, debugging, auditing, and improving model becomes impossible. MLflow solves this problem by acting as the system of record for experiment and models. So let's walk through uh, what what actually we are going to do step by step, and why, and at the same time I'm going to explain you what each part is doing. So first thing, we are actually going to install the Helm, install and upgrade. So we have already actually updated the Helm. So let's do one thing. Let's first upgrade Helm. So let's type. Oh, sorry, it's Helm. Oh, so first thing first, uh, we actually need to we have not added the any community charts. So let's actually bring the Helm community chart. So let me, then we can actually run this command. For that, we can type Helm repo add community charts, and you can, there are many community charts that you can I am going to use Helm charts. So let me paste the URL, and let's, community chart already exists because for me it's done. And then we can do the Helm repo update. Helm repo update chart repository. Now we are actually going to deploy the MLflow. So since for me it's going to throw an error, I already have the MLflow. So a good practice is to first kill the existing one. So you don't need to, but I am typing this command because since once you are going to uh, kill, I mean, we need to avoid any port forwarding already in use uh, Kubernetes clusters. So let's kill, because you are going to see such errors of port already taken. So before installing that, let me remove existing, and this is going to be very helpful for you as scv slash MLflow. If you face any error in this lecture, try to run this command. uh, it doesn't do anything, it won't do for you as well because we haven't installed the MLflow. So let's bring hyphen hyphen install MLflow and community. So I'll explain you what we are actually doing. So we begin by adding the Helm repository using that command Helm repo add community followed by Helm repo update. A Helm repository is a simple collection of pre-packaged Kubernetes applications called charts. By adding community charts repository, we gain access to production ready MLflow Helm charts that already encode best practices for Kubernetes deployment. So next step, what we are trying to do is here is to deploy MLflow itself. We do this by using Helm upgrade in hyphen hyphen install MLflow community hyphen charts slash MLflow. So this command is important. The word upgrade means deployment is idempotent. If MLflow already exists, Helm will upgrade it. If it does not exist, Helm will install it. This is what we want. This is the core MLOps principle. Infrastructure should be repeatable and safe to rerun. Now, the next step is, let's go to second line, and now let's define something. Uh, mhm, we, yeah, so what we are going to do is we are going to deploy this into the dedicated namespace called MLflow using namespace and MLflow hyphen create hyphen namespace. So namespaces are logical isolation mechanism in Kubernetes. As our platform grows, having separate namespaces for MLflow, Airflow monitoring will keep the system clean and manageable. Now let's talk about the backend configuration that we need to do. So till now, I hope I don't, although it's two line, but they are very important in terms of keeping the best mm, best practices. So now what I am going to type here is something that MLflow requires. So MLflow needs a store to persist experiment metadata, and we can enable Postgres by setting Postgres equal as true. So what how we can set, you have to use hyphen set back end store dot data basis database migration equals to true, and that's how uh, by this is what we have to type. So what this will do, this is going to create the Postgres database inside cluster specifically for MLflow. We also configure credential using Postgres auth.username. So that's something you can again use these hyphen set and then Postgres. Let's Postgres 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 QL dot L equals to true, and let's also set SQL dot auth dot password is going to be it should be a long uh, very long complicated string, but for now I'm going to type password. Don't do that in production. This is just for me trying to set things quickly. Dot auth dot username is going to be MLflow, and again set PostgreSQL dot auth dot database is equals to, let's create the database with the same name. All right. Once this is done, we also need to enable database migration by setting backend store database migration to true. That we have actually done. So what this is doing, this ensure MLflow upgrades its schema. The database should stay compatible. Next is the artifact storage, which is one of the most misunderstood part of MLflow. Artifacts are the things like trained model, plots, serialized file. We configure MLflow to use proxied artifact storage by setting artifact root proxies flag to true. Then we define the default artifact location uh, to set the artifact directly to ML artifact. So what we are going to do is allows MLflow to serve artifact through its own server rather than exposing raw storage directly. This mirrors how MLflow is typically deployed in a secure production environment. So let's do that. Artifact, we have to type artifact root dot prox. I hope that I'm spelling everything correctly. Proxied artifact storage equals to true. Perfect. Now we have enabled it, and now let's di float dot uh, default storage default artifact root. Let's set this to MLflow artifacts slash ML ML artifacts. Great. And uh, so final thing, now we also need to pass the environment variables and flag for MLflow server. What what we in this setup, we allow the MLflow UI to be accessed from local browser during the development. So this is something which is not recommended for that I'm going to do for the prod environment. But yeah, this is something you should do for only for local development. When you are doing the deployment, you can specify the IP ranges that you are going to allow. For now, I am actually going to set the environment. So this something is called extra env wars dot ml flow. Don't worry about the codes, and I'll make sure that I'll commit all of the files, uh, so you can copy paste from there. In case if I'm going to make any typo on that file, it will be corrected. I'll make sure that. So understand that why we are doing this, because this is locally and we want our UI to be accessed. And now what we are trying, next thing we should do is to bypass is by serving like we enable uh, the artifact serving by passing server artifact using extra flag, and we define the local artifact destination using again extra var artifact destination as temporary ML artifact. So this is something also we need to make sure that where we are going to store the extra env, sorry, it's extra arcs dot artifacts and destination, and then the path name slash And let's also set extra flag 0. Artifact. So make sure that this command is ready, and let me actually, I have made one typo, and let me copy paste this thing. It's extra flag 0 server artifact. Extra artifact. All right, let's do one thing. Let's create a file. Actually, it's better you create. Anyways, I'm going to ship this. So let's add the command that we are going to run in the sh file, and let's also do one thing. Once the Helm is going to actually install, Kubernetes still needs time to start the pods. So let's do one thing for kubectl. Let's wait it. Wait -4. The for condition that the above is ready. And we need to tell uh, that it is a name with the MLflow. So let me actually grab that command. So this is what is going to wait for MLflow, and it will time out after 5 minutes. This much time we are going to wait for the MLflow pods to be ready. What essentially this command is going to do, this command is going to block until MLflow pods are actually ready. Without this step, we might try to access MLflow before it is available. So next step is, this is for, again for the local, you can omit, but better to learn. In the prod environment, because it's a local Kubernetes cluster, and we use kubectl port forward. This maps the port 80 of MLflow service inside the cluster to the port 8081 of your local machine. So you can open the browser and see your MLflow UI without exposing the service publicly. So this is something which is good practice. So let's do that. And once this is done, let's actually print MLflow is ready, and let's also print the address. It's actually good practice. Host 8081. And I believe now how we are going to run this. You can make it executable. X dot MLflow setup. Oh, wrong spelling. Chmod. Now we can run this file. Perfect. Now let's wait for it to install the MLflow. Then I'm going to show you the MLflow UI, where you will show you where will all the experiment and all will be present. So in this channel, I have made an extensive course on MLflow. So I assume that you have watched that, but if you have not, I'll link the complete series to this video, because this is an upgrade to that video. And uh, because now I'm going to write a training code which essentially required for us to have the working knowledge of the MLflow itself. And this much is actually, I would say, this is all a bit advanced course. So if you have any confusion of what I am going to do the next, you should probably watch that series, and it's going to be very helpful. So let's do one thing. Since I need to run the uh, model training, usually it's separate environment, but I'm going to use that same folder. And then what we are going to do is create a virtual environment and then write our training script, connect to the MLflow, and connect to the MLflow that we are actually in the process of creating. Run the training job, see if that training job is working, and this much how to connect with that. This much we are going to cover in the same video. So let's do one thing. Let's create UV, VE, and V. Oh, one thing. Let's do UV init. It created an activity. Let's create UV, SY, and see. It's going to make a virtual environment. And also, if you don't know what is UV, then again there's a video in this channel to understand what I'm doing here is just creating a Python environment. Perfect. We are using our environment. Let's come here and let's rename this file to something train ML flow, and I am actually going to add some dependencies. So uv add MLflow sk scikit hyphen learn. Let's also bring pandas. Yeah, that's pretty much. We are going to keep that lightweight, and let's run it. It's installing. Let me bring our data. So this is our diabetes. Uh, it's going to predict this target variable, which is this is the target variable. This is our feature vectors, and we are not going very deep into that because our objective is to train this model on that target variable. And I'm going to use a very lightweight model for that. Uh, so let's actually go and start doing things. Let's see if our MLflow Helm is done. Perfect. As you can see, our MLflow is working. Do we have an experiment? We don't have anything right now. It's a clean slate. We can start. If it is working this much, that means you are ready for writing the MLflow code. So first thing first, let's import MLflow, and let's if name main. That's very important, and we need to configure MLflow to point to our K8 instance, because MLflow is running on Kubernetes. So let's use it in the way that it is meant to be used, by tracking a real machine learning experiment. I am going to walk you through this training script, and I want you to notice something important. Although there is nothing toy about this setup, this is exactly how MLflow is used in real production pipeline. So let's start with this. Let's first open the tracking URI, so we can get this from OS. So also let's import os dot get env MLflow tracking URI. We will get from the environment, but if it's not able to find, then let's also give this a default value, local host 8081. Perfect. And then we can set our client, set to tracking URI as tracking URI MLflow dot. Now we can set the experiment name, experiment as since let's call it, we are going to use elastic net model, so let's call it diabetes elastic net, and let's call it v1. Perfect. Now let's import our data from the folder. Let's mark the data path, the data is in the data slash CSV, and there is a huge possibility in our cluster this path won't resolve. So let's actually so let's do one thing. If not, os dot path dot exist, if this path dot does not exist, and then we can need to, what can we do? And then in that case, can we create the database itself? So let's do one thing, because I want to show you, like, if your data, there is a you need to provide a possible pathway for our data to exist. So let's create one more file. Let's name it export data.py, and we will keep our separation of uh, loading the data from the training code. So for now, from sklearn dot datasets, let's use some pre-built data, load diabetes, import OS. So let's define export data, and then let's load the dataset, and then you can use let's import also pandas as PD. So pd dot data frame diabetes dot data and columns diabetes dot feature names, and we can define our target diabetes dot target. Perfect. os dot make directory slash, let's make it as data, and then exist. Okay, true. And second thing is, let's also define the data path. Same, we can also take it from there, but diabetes dot csv df to csv data path comma index. Let's not give it, and let's print data creation done, and if name is equals to, then we can call our export data. Let's export. Let's test this. I'm actually going to delete. Let's delete this and UV run export data. Hopefully we will be able to create the data set. It's actually downloading it. What is happening? Perfect. Yeah, we have the data, so nothing to be worried. Now we can come here. If the case where our, so we were trying to handle, if our data does not exist, then in that case, let's import. Should we do import? Yeah. So from export data, import export data, and then we can call this function, and let's also import as dt df is equals to dt dot csv, and we can pass the data path, and x is equals to df dot we can just drop the last column, and in x is equals to 1, 0 is the row, and we can get df, actually we can get the direct target. Perfect. Let's call, okay, let's also from sklearn, let's get the train test split. So I think it's in the sklearn dot model selection, import train I believe it's in the oh, sorry. Trains test. Also, let's import some other dependencies as well. sklearn.matrices. Let's import mean squared error, and also let's absolute error also, and let's also measure R2 score. Perfect. This much we will require. And when this is done, so let's create the train X, train Y, train X, sorry, it's test X, test Y, train test split. Let's only pass the X comma Y. All right. So now we have the data. We can start the training. Let's define the important parameter for training. 0.5 for alpha and 1 ratio. And now, because why I'm doing this, it's not important. I want to actually load some of the parameters in the MLflow. MLflow dot start run. In this context, this is important. In this context, we are actually going to we have not imported the model. Okay, let's do one thing. From sklearn dot linear models import elastic net. Perfect. Elastic net. And then we have to initialize this. Let's define the alpha and L1 ratio as L1 ratio, and the random state for 1, 2, 2, 2, 2, 3. Fine. And let's call the fit method. This is actually going to train our learner. lr dot fit. Let's pass the train X, comma train Y, and we can now actually, as we do this, when this is done, let's loss prediction is learning dot predict on test X, and we can now let's make one more function outside this. Let's call this eval matrices. Def eval matrices actual versus predicted, and let's call the RMSE is mean squared error, and we can pass actual comma predicted and take the root square under root. Mean absolute error, again let's pass actual predicted, and let's calculate the R2 score. actual and predicted, and let's return RMSE MAE and R2. Perfect. Let's come here, and now we can actually invoke this function, and let's call the eval matrices. So the actual value is the test test y comma pre. So what this is going to do, it's actually returning three things for us. First thing is our MSE, MAE, and the R2. Now we, since these things are important, so we are actually going to log them. How can you log it? So you call the log param, and let's log alpha. Let's copy and paste this multiple time, and let's L1. Why I'm doing this? Because for this experiment, these were the values RMSE and then MEA, then we can call R2, and then we can call the R2. Perfect. And once we'll log the parameters, let's register this model. So mlflow.sklearn.log model sk, there is called sk model is the LR, and then artifact path is model, and registered model name, let's give this name as DEM, and let's print done if everything goes well. Whew. Let's go run it. UV run train MLflow.py. Hopefully there is no error. One thing that I did here, for some people it might maybe they can think why we are not uh, written in the same function. So it's actually, you can perfectly do that, and separating this logic into a function is intentional. In production, metrics calculation is part of your contract. You actually want it to be isolated and reusable and testable. So because of this, I have moved that out of the main block. Let's give this some time. So also, like, meanwhile I'll explain you what this is. So here, Everything that happens inside this block is automatically associated with a single experiment. Think of this as a transaction boundary for your machine learning job. Inside this run, we are initializing the elastic train models and then generating predictions, then compute metrics. At this point, this this is something we have done, and then logging the matrices. Finally, we were calling the sklearn log model artifact path, and we provide the registered model name. So far, so good. This single steps promotes the model from just file to a managed asset in model registry. So from this moment onward, this model has version, lineage, matrices, history. It can be promoted to staging, production, or rollback, exactly like a real production ML system. At once this is done, our experiment should get log here. Let's wait for this. So what I wanted to show you is you people to realize that MLOps is not abstracted. It is concrete and inspectable and auditable. And this is, by the way, just the beginning. In the next module, we will build automation pipeline on top of this, turning individual runs into repeatable production grade workflows. All right, failed to get mixed retry existed. So I can see there is a connection issue. Get by name. Oops, sorry. Because of that simple typo. It should be localhost. Okay. Sklearn. Oh, sorry, it is log model. It's better that we are getting some error. All right. Yes, that's what I mean. Perfect. Let's see. Yeah, finally we can see. So look, our failed experiments are also here. Our past experiments are also here. And you can see them. Model matrices, traces, artifacts, conda, model file, and its requirement, what it requires to be get installed. Environment also. Everything like from this onward, this can be reproduced anywhere. Like, and we can see this model is registered with DEM, and all of the informations are here. Input, output. This is something that we have covered in more detail to how to populate these things. And yeah, you can follow that lecture for more detail, deep dive into the MLflow. But for now, our base is ready. we won't be writing that much Python code again, because next thing we will be uh, managing this through the K8 as Kubernetes. Yeah, one more thing is how can we serve this model over the API. So for that we are going to write the Flask API. And yeah, thank you very much. Let's move to the module 2, where we take the model we trained and tracked with MLflow, turn into real scalable service running on Kubernetes. This module is where the mental shift really happens. Until now, we trained model and tracked experiment, but a trained model that cannot be served reliable is not useful in the real world. That's the actual crux of this course. And the model must handle traffic, recover from crash, scale when demand increases. This is exactly this is why Kubernetes exists. So let's talk about why we are doing this. So you cannot run a Python script on laptop and expect it to serve millions of users. So process can crash, machine fails, and traffic is unpredictable. Kubernetes solve this problem by managing containers for us. If a container crashes, Kubernetes restarts it. If traffic increases, Kubernetes can run multiple copies of the same model server. Uh, Now let's talk about what we are going to build here. Um, we are going we will start a model server, which we will write in a very simple Flask application. This server does something very important. It does not bundle the model inside the Docker image. Instead, at startup, it should connect to the MLflow inside the Kubernetes cluster, fetch the latest version called DEM load into memory. This is the key pattern that we should first do, then we'll talk about later. So let's make the file app.py. Let's go inside that file, and first thing first, from let's add Flask. Let's import Flask quests and JSONify, import MLflow.sklearn, import pandas as pd, import os. Let's make our Flask, sorry, Flask under name. Now let's define the URI. Let's go ahead and copy it from our training code. Same thing. And model code name. It's what we had our model DEM, and let's MLflow dot set that score tracking URI. Perfect. ML URI. So this much, as we run this file, this much will be done automatically. So let's make our function which is going to load our model. So let's put a try exception is equals to F. That's how in the models artifacts path you can pass the model name slash latest. So what this is actually going to do, it's going to because we are going to run it this many times, so it's actually going to bring us the latest model file, latest version. So let's make our MLflow client MLflow dot tracking dot ML. I believe it's tracking and tracing is different. Tracing is for AI and LLM inference. MLflow client. Now let's get the latest version. So client dot get latest versions, and we can give our model name. If not latest version, so we can throw the error model not found. This is important because if your Kubernetes paths are not correctly set up, it could be a cause why the model will not be getting loaded, and this debug statement will help us for such issues. And we can like in that case we should return none, because like now let's get the model. So MLflow dot sklearn dot load model and the model URI, and then we can return. So this much is important because this is something the uh, MLflow stuff except exception is E, and then we can print any error if it occurs. Let's print the error. If you see any error, you can you can comment down these in this channel. Uh, if you see any error, I'll help you in resolving those, or if why that error occurred. So now what we need is some paths that are actually going to help us in making predictions, like slash predict health path, where a machine is healthy or not. So I see a lot of people what they is like, if the slash health API is responding, then they assume that everything is correct, but no, you should create your let's first make our global none, so that we are able to access it. The best way of making our health, because it's going to be very useful, your API can be up, but your machine learning uh, models are not ready. This is a real problem, and I have seen a lot of people make mistakes here even in the production, and that creates really a lot of problems. You can have your machine getting scaled and still not serving. So we are talking about real problems here. So how should you do it? Let me show you. uh, so usually people return OK 200 here. What you should do is only return these status HEALTHY and model loaded as the variable. See, this is important. So there are two things. Your API is healthy, good, and you should run your loaded as model is not none. So it will tell us true or false. If model is actually correctly loaded, then you know correctly what is happening inside your container. Like, so make sure this you do that. And let's, and to save your time, I'm actually going to walk you through the predict code. And see, slash predict, it is a post method, and we are taking the global model. If the model is not present, it's going to load the model. If model is not, we should also return the MLflow. Is the ML registered or not? Get request, get data frame, model.predict, return the prediction. Python is just the simple machine learning stuff. Nothing fancy here. All the idea should be we should be able to check if everything is working fine, and we should be, if we are able to make the predictions. So let's, I am not going more in detail into that because we have to build in this tutorial. I wanted to build the Docker container and all, and that's only possible when we can abstract away some of these things. So let's start this server. And also one more thing, like you will see sometimes these uh, statements will not come, so make sure to make flush as true, so they'll get, as this execution happens, this your, you should be able to see I faced this. If you are not seeing the logs, then just make it flush as true. So make sure if our API is loading, we have a model, and then we can run dot run. Let's go host 0.0.0.0, and let's run this on port 5001. Perfect. We have created a Flask server which is going to serve our model. And once this is done, let's create our Docker file. douch file. We have our Docker file. This is actually going to build our API, and that API is actually, it's just spinning up this Flask server. So let's bring a Python 3.9 slim base image, kdir/app, copy stars.txt, and okay, we'll also create a requirements.txt first. It requires MLflow, pandas, and Flask. What else we were using? MLflow, Flask, and let's also like it scikit-learn, and also a Postgres dependency. G2 hyphen ps psi copy G2 binary. Perfect. And now let's come here copy this requirement, run pip install, and this one is no cache, -r txt. Hope this is correct. And then copy app.py into the working directory, expose the port. Let's run the command python start app.py. Awesome. So the thing we have done here is we have created our Flask application, and then we have created the Docker file. So let's first build our Docker uh, image. So Docker build -t diabetes model server latest dot. All right. Oh, sorry, I forgot. So yeah, it's building, and hopefully we will be able to build that. Once this is done, then we can load the image into kind, which is Kubernetes and Docker. Since kind does not use a shared repository, we must locally load the image. And once this command is, it's no cache dr did not complete. All right, let's see. Because we also need to write our Kubernetes manifest, and I'll actually, once this is done, we'll go there step by step. First thing we'll do, load. Once if this runs successfully this time, we are going to create. Okay, there's an error. All right, let me dissect this. Did not complete it. Maybe something here. Be the requirement are not correct. Let's try one more time. Then we can see the problem here. Perfect. It worked. So the problem was in the requirements file. All right. So now that we have our, we can now load this Docker image into kind. We can pass kind load Docker image type. It's type PETES. I hope that I have not made the typo. slash model slash server latest. This is what we have built our image. That's the name. Cluster 1. So we have to do this. Image with ID not present on cluster control panel, loading not at present. Perfect. Great. Now we can create our K8 as manifest. K8 as manifest.yaml. So this manifests that let me copy. I'll explain you what is happening here. So this manifest defines three critical things. Deployment, which manages replica pod for our model server. A service which provides stable network endpoint. A label selector that ties everything together. So when we are going to run the command kubectl rollout, this ensure the latest image and configurations are picked. Kind, we are going for deployment. This is the server and we are going to use default namespace. Let's make one replica, and this is the image name that we have selected, and this is the container port, the MLflow tracking URI through internal networking. This is the establishment of internal networking between the pods. And now once this is a standard template, actually you can get it from internet. This is how you do configuration. For us everything is matching here, so what we can proceed with our next setup is to apply the skate manifest kubectl apply -f k8s manifest yaml. Perfect. Now we can kubectl rollout status deployment slash diabetes model server, and let's time out. It should not take more than 2 minutes, I guess. Let's put 120 seconds. Successfully rolled out. And now for local testing we need to actually do port forwarding. So let's copy the port forwarding command. So we should map let's first no it won't work. Let's kill any existing port forwarding. I'll actually paste all of this in a uh, uh, file, so that now what we are going to do is to develop a mapping from 80 to 500, one of this to 5002. Now we can actually go there and in our browser let's test ctp /localhost in over port 5002. We have ported 5002 health. Yes, perfect. Our model is healthy. API responded. That's actually we wanted. And now we can actually test our model, if it is making the predictions. So let's make a post request to that server. So it's a curl request which is going to pass the age, sex, BMI, BP, S1, S2, the feature vector, and we got the prediction. So much hassle for all of this, but this is important because what we are doing is the deployment is to become ready, and this is not for just for the convenience. It's a actual production pipeline. And so uh, provide the all of the commands in a file, and in case you see 403 message or ab- about invalid host header, when model servers, what happens when model server talks to MLflow, this is due to MLflow security middleware blocking internal uh, Kubernetes services. You might see 403. The simple fix is, uh, if you remember the way we have configured uh, the MLflow, so on that case, delete that pod of MLflow we have created. Uh, Kubernetes will already automatically recreate the new pod. The server is going to fetch the new model again. One important reminder here, the model's server depends on MLflow being available. Make sure that your MLflow service on port forward from module 1 from the previous lecture is still running before running the server. So that's why you can see my terminal is still running. You can inspect how you can inspect it. So you can type kubectl get pods. See, your pod is now running, and you can also get the logs. What unexpected log? Oh, you also need to provide which pod. Let's try. See, you're getting the logs from there in the of the pod. So kubectl is very helpful. Uh, and at the end of this model, we have achieved something very critical. You trained a model, you tracked it by MLflow, you registered it in the MLflow registry, and now you're serving it as a scalable self-healing APIs on Kubernetes. So this is the core of real world MLOps. In the next module, we will go one level higher and start orchestration workflow and automation on top of this. So really excited for the coming up lecture. For the This time we are going to introduce you to the airflow. Thank you. Move to module 3. There we are going to introduce into our in orchestration into our MLOps system using Apache Airflow. Up to this point, we have done three things: set up Kubernetes as our execution environment, use MLflow to track experiment and manage model. We deployed a trained model as a live service, but there is still a major gap. Right now, training happens when you decide to run a script. That does not scale in production. Humans do not trigger training job manually, system do. This is where workflow orchestration come in. In production MLOps, you need four guarantees. First, scheduling. You want to retrain a model every Sunday night or whenever new data arrives. Second, Sunday is just Sunday. So you can pick any day. Second, retries. If a node is busy or pod fails, the system should retry automatically. Third is dependency. Training should never start before data preparation finish. And fourth is the visibility. You need a clear visual view of what is running, what failed, and why. Apache Airflow is the industry standard tool that provide exactly this. Now let's talk about what we are building in this module. We are going to install Airflow on Kubernetes, just like we did the with the MLflow. We are going to use Kubernetes pod operator, which is recommended best practices for machine learning workflow. And we are triggering a training job that runs inside our fresh Kubernetes pods and logs everything back to MLflow. And before that, you need to learn the basic concept of DAG. So a DAG is a directed acyclic graph. This is just a Python file that defines your workflow. So in our case, let's right away create a file .py. So hope it's created. Yeah. Uh, Inside this, we are going to define task, and this task does not run Python air code inside Airflow itself. This is very important design decision. Instead, it tells Kubernetes spin up a brand new pod using MLOps image that we have created and run a training uh, script inside that container. This is exactly how modern MLOps pipeline should be built. Airflow should become the orchestrator, not the execution environment. Kubernetes should handle the execution. Containers should handle the dependency. So let's build our uh, Airflow. So for that, let's do one thing. Let's first build our ML that tag. So I'm actually thinking what should we do first. All right, let's build Airflow first. Import Airflow. Let me add UV just for the sake, so that you don't see the errors in IDE. It's not required, although. Let's give this some time. Oh, should be done. Perfect. From air data in Airflow import DAC. From Airflow dot providers dot cn cn I believe it is cncf dot kuber leds dot peratur operators dot pod. I believe it won't work if we are actually going to run .tst. All right. let's actually so I think it's not going to work. First, I don't want to create some confusion, but let's go in the order. Let's build our dockerfile.mlops, a script that will start building Docker images. This image will contain everything required for training: Python, scikit-learn, MLflow, training code itself. Once the image is built, we will load into kind, and the kind so the kind actually do not sees local Docker images. It forgoes this step. So Kubernetes will keep using our old image, and your so so the idea is to what I wanted to do first. Let's create the namespace of Airflow, because namespace is going to give us the isolation. MLflow will live in its own namespace. Airflow will live in its own namespace. This will keep the system clean in production. And the very important part is the RBAC, or role-based access control. This is why I stopped writing the code right now, because Airflow needs permission to create and manage pod. By default, it does not have that permission. So we create a role that allows action like create, delete, get, watch on pods and pod logs. Then we bind the role to Airflow service account using role binding. Without this step, Kubernetes pod operator will fail silently or with cryptic permission error. So, uh, so, uh, so here, like we need to create a config map, uh, which will ensure that these things are happening correctly. And so so that uh, it's bit complicated. So let me do one thing. Let's actually create airflow hyphen values dot yml, and let's try to first fill that up. So let's bring the executor, return and test it. So this is a, I would say, bit tricky part here, and this configuration I have actually taken from internet itself. And what I'll tell you, the changes that I have made is this is the file name where your actual DAG lives. This is important. And in the DAG volume, you also need to mount the path. This is the only thing that I have changed. The path. This is important because what we are running here should be run in the Kubernetes clustered. So, and this is very standard thing. If you want to get more deep into this, you can go, but I'll rather for ML, we can make another video for details into that. So for example, for now, let's make things bit simple, and let's create a entry point file, which is going to be the, let's call it run pipeline, pipeline dot sh, and let's open it. This file will only, let's add bin bash, and run pipe. So later on we are also going to modify this file. This file will check if we have data change. So but for now, it's very simple. It's going to call this function that we have created, train MLflow.py. That's the simple file. And then we can make one more file, touch docker file dot MLOps, and there we are going to write how to run this MLOps pipeline. So from Python 3.9 hyphens lim is going to be the base image, work dir, let's app, copy requirement dot txt, run pip install minus no cache dir minus r requirement dot txt, and then we can copy the training script, flow.py, and we can also copy py, because this orchestrator should have everything, like how to make the APIs and all stuff. Run pipeline.sh, and let's also copy the data itself, data slash diabetes.csv into the folder data. This is important because we have written code like this. And let's also make this executable, the run file chmod pipeline.sh, and then we can just run this command, pipeline sh. Perfect. So what we have just done is making sure that we have our required codes available to us before we are going to load the inside the kind. We can first pass our diabetes model. So let's do one thing. Let's build it. So docker build minus target diabetes model server latest dot. So this Docker file, it's going to build. Perfect. And then we can load the same step that we have done. Docker images, type it, and type it is model server latest, name as MLOps cluster 1. Let's server, believe must have made some typo. Let's try again. Oops. All right. So it is already loading. So I just wanted to make sure that we have done this much. This much should be done to run what we are going to do the next. And so we are actually going to build this file, diabetes MLOps latest with Docker. Copy. Oh, so this is, yep. I believe I have, yeah. So, and we can load into our cluster, same thing. We can load, and then we can we need to create the Airflow namespace and RBAC role-based access. So for that you can type kubectl name space Airflow. Let's make try run. It's actually going to take some time. -o YAML, and then kubectl apply -file, and the and then there is a command, although I tried to make this work. All right, so it's going to be a bit clumsy. Let me try to run this in the set airflow. Let's run this. What should I make? Setup dot search, and let me try to bring the command one by one over here. So this much worked. Now what we need is the kubectl. I'm actually going to explain you. So the thing that I explained is pretty much these things where you need to have the get list watch create permission, and this is what we are doing here. And then RBAC, uh, the namespace should have these I mean, or web server should have these operations. These these things are again pretty much standard. I have not made anything changed. If your namespace is different, then you can just change the namespace here. But uh, you should understand, like, the RBAC, why it is important, because Airflow needs permission to create and manage pod. Without this step, the thing that we'll try to write in our Python code won't work. And then once this is done, let's go and using kubectl, we'll create uh, this client, and we can install using Helm. We can uh, bring the Airflow chart, and then you can also doing that after is important to update. So we use value file that we just have created for the Airflow. In there, it's important to, because it's important to have a correctly mounted for mounting of our DAGs, and that we have defined in the Airflow hyphen values. So this is important. And Airflow setup, and then we can wait for the server to load. Same thing that we did, if you remember, for MLflow. Wait for until this is done. This is going to take actually 5 minutes, and we can create any existing one because I actually have one running, and then we can port forward 8080 to 8080, and we can then echo if everything works. Then EC no echo Airflow UI at tp slash closed 8080, and you can pass the password admin. And then now we can start building our, let me actually bring, because this session is getting quicker. So yeah, we need to bring from CNFCF operator pod, Kubernetes pod operator, the arguments, who's the owner. It does not depends on any past. Start date, you can mention email on failure. This is standard configuration. This is the default arguments, and then this is how you define your DAG. This is diabetes training Kubernetes train diabetes model description, and manual trigger. Do you want for schedule interval? If you want, you can provide a cron expression over here. So now this is the pod operator. You need to define your namespace, the image that we have built, and then it runs train.py and label this as diabetes training, and image pull policy will use kind cache, and then you all in environment, since we are setting up the uh, MLflow tracking URI. So this is something we can pass as the environment in that Kubernetes pod. Very important. So I think now we are pretty much ready on. Let me see if everything is correctly done. So once this is done, let's make it executable. // airflow setup.sh, and let's run. All right, it was a difficult one. Okay, I believe we have made a change. And so the cluster name is this. Let's cancel this again. Small mistake. For you, I mean, you can prefer to omit one, because since I have run this one, actually I'll also teach you how you can delete it. So I mean, in future rather you can just change. Let me quickly see my all. Yeah, we won't see any error. It's going to take some time, and let this take some time. About, it's going to actually take 5 minutes. Let me pause that, and from then I will begin again. Okay, so Airflow is installed, and let's try to open it. Okay, I can see my DAG over here. Let's enable it. For now, you'll only see one node. You can chain it with multiple steps, but this pretty much has everything. It's going to train our model. So let's run it. See if it is working. Let's click on log, and it is running. Perfect. Our model has trained. Let's check MLflow and verify if we have another version. That's exactly we wanted. we have just achieved Airflow. This. So if you understand, if you are paying attention, what just has happened, the model is not trained through running something here in this Python terminal. No, actually we have spun up a pod. There the pod was created, deleted, trained. Airflow is doing everything. So what it is doing, it is asking Kubernetes to create brand new pod using diabetes MLOps image. This pod will run training script. Script will talk to MLflow, matrices, parameters. Model will be logged exactly like before, but this time no human ran a Python command. If you click on the task instance and open log, you so you can see it's here. Version 2 is here, and one key insights here is the isolation. Airflow itself does not need scikit-learn It does not need MLflow installed locally. It only needs permission to ask Kubernetes to run the container. This completely eliminates dependency conflict and it works on any machine. One important reminder, if you change training code, you must rebuild the Docker image. So for that, you can run kind load Docker image. Otherwise, Kubernetes will keep using the old images. At the end of this module, you now own a fully orchestrated MLOps pipeline. Training run inside the Kubernetes, execution is triggered by Airflow, experiment and models are tracked by MLflow, and everything is in front of you. Everything is running locally. This is the same architectural pattern used in matured machine learning platform in production. I just shown you a glimpse of it, and a production graded control that turns into true end-to-end MLOps platform. So this is where most, I will believe, most of the machine learning educator might have reached. To show you, we are going to take this to the next level and introduce something called monitoring. So in the next module, we are going to learn how we can integrate Prometheus and Grafana in our MLflow project. Thank you. Monitoring, where we add uh, bring our MLOps platform. This module is extremely important, and it's also where many machine ML system fails in real world. A cluster that you cannot see is a dangerous cluster. If a training pods get killed because it runs out of memory, you need to know. If ML flow goes down, you need to know. If training time suddenly doubles, you need to know. This is why monitoring is not optional in production MLOps. To solve this, we use Prometheus and Grafana. Prometheus is responsible for collecting matrices, things like CPU usage, memory usage, pod restart, and service health. Grafana is responsible for visualizing those matrices into dashboard that human can actually understand. Together, they form the industry standard in monitoring stack of Kubernetes. Now let's talk about what we are going to do. We are not actually going to install them manually. Instead, we will install something called Kubernetes stack. This is officially the production grade bundle, including, you can search on it as well. And this is a very well known, an official production grade bundle that includes Prometheus, Grafana, Alert Manager, and all Kubernetes export needs to collect matrices. This is exactly what most production Kubernetes cluster use. So uh, let's start building actually. And let's also, I actually like this way of doing creating the shell script. So let's do also this time as well. Monitoring setup.sh. So so first thing first, uh, we need to upgrade our Helm with these Prometheus. So let me bring the command for that, and I'll explain you each thing. Actually, before that, we need to upgrade the repo. We need to bring the community. Let me also copy paste that command. So adding the Helm repository, and then uh, so what we are doing is Prometheus community Helm repository. We are adding it, and followed by a Helm repo update. This repository contains Prometheus stack chart. So and to avoid any port conflict, uh, So this is what we have been keep doing with Airflow, MLflow as well. We'll kill all of the previous one, but do not do that in prod. This is for local only. You can avoid that. Now, uh, now we will be installing the monitoring stack using Helm. So what is happening here when we run the Helm upgrade install Prometheus, just like before, this makes the command idempotent. You can safely run it without breaking the cluster. So we deploy everything into a dedicated namespace. See, we are creating the namespace as monitoring, and monitoring is resource heavy, so keeping it isolation is a best practices. We explicitly set Grafana password. So now it's admin. You can obviously you'll change it. This is fine for local development. In production, this would be managed securely. Next, we set two Prometheus configuration flag. One is the pod monitor select monitor nil user helm value is false, and selector nil user helm service for service monitoring, for pod monitoring, for service monitoring. These flags tells Prometheus to actively discover pod monitor and service monitor across namespaces. This is what allows Prometheus to automatically scrape metrics from Airflow, MLflow, and other services without manually wiring. And this will see the magic, because I am not actually going to tell our the Grafana. Everything will be present over there. Once the Helm will start deploying the stack, Kubernetes needs some time to spin up everything. So let's add a wait. Same thing, we will wait for monitoring namespace for 5 minutes. This ensure that UI is actually available before we try to access it. After Grafana is ready, we'll actually need to enable port forwarding for this, because this is for the local step only. In 3000 port, we should be able to then view it. So let's make this file executable. Monitoring setup, and let's run it. Monitoring setup.sh. All right, it's installing. Should take some time. Let me pause that. We can connect, like our server is up. So I'm actually very excited. It's on port 3000. Let's put the password. Let's skip it for now. Let's go to dashboard and space prod, and we should see, yeah, can you say this? Airflow, it knows Airflow, it knows MLflow, and it's taking care of all of these things. Airflow server, Airflow trigger, Postgres scheduler. Let's actually run it again and see if we are able to record any data. Let me trigger it, and you see, in real time we are getting, right now we are getting the last coverage. We should see data, and let's see our MLflow. Oh, perfect. Now, as you can see, all of the data are coming. It is very actually good. Again, let's check the airflow. It's great. and default namespace, kube systems, local path storage, monitoring itself. Perfect. This is what we wanted. We wanted to see our dashboard is created for us to monitor everything. Yeah, I mean, that's really awesome. See, if we are exploring our MLflow, it's all up. You can see as we get more data, these charts will get populated. So it's first. This is very important actually. That right now what we have done here. And thank you very much for watching this. Next one is we are going to combine everything and we will see everything as one system. We build individual systems, uh, Kubernetes, Airflow, MLflow, model serving, monitoring. Each one is powerful on its own, but real MLOps value comes when all of them work together as one integrated system. So this video is about proving that integration. This is the moment where we run complete MLOps cycle end to end with no manual glue. Let's start uh, uh, of what we are going to build. It's and not something very technical. The purpose is the observability. It helps us confirm that every part of system is alive before we trigger the pipeline. So let's build one script and let's call it op.sh. And what we are in this, what we are going to see if our MLflow, uh, if we actually have our model uh, with us. So let's do one thing. Let's type in bash and we can make a curl to our airflow server. And so let's call our airflow server to get the latest register model. We already have made the name, and let's actually print. Let's pipe this to Python script. Python 3, the output of this -c. Let's import system JSON, and let's just print dot JSON dot load sys dot stdin, and we can whatever input we are getting, let's JSONify and load it. Let's try to make it executable. chmod x dot observe. Let's try to run it. Okay. Oops. Yeah. So you can see we have our model present. So this verification is done. And now let's check our airflow. So MLflow is working. MLflow is working. Let's check airflow. So we can, with the help of kubectl, we can get config map Airflow X Airflow. Let's check. Server does not have resource config. Oops. So I sorry for that. We should be able to. Yeah. So our Airflow DAG is also fine. Great. And then we need to check is our API working. So remember, we have made a health checkpoint. So we are going to run that. 02/health. All right. So now we can just bring this command over here. This is going to check if, and also let's do one thing, because this could be an independent thing. So let's echo if this fail. API is not working. That be fine. Yeah. So if we have some error, then this is going to print uh, this. Now let's check if our monitoring is up. So again with kubectl we can do that. Get pods, and namespace is monitoring. Let's grab. Let's actually first run it. See what information we can get. And let's check if Prometheus Grafana is running or not. Grab nice. So our Grafana monitoring is also up, and once if we are able to see this echo, this is ready, can trigger the flow. Obviously we are manually triggering, but you in your DAG, if you can specify the manual trigger, then that's also fine. Now if you run it, system is ready, you can trigger the airflow. We'll trust this and let's try to trigger it. If we get an error, uh, let's say if we get any error, and it should register the third version. Perfect. Perfect. So service is running, model is loaded, service is ready to run. The API is also serving, and you can also monitor it through your Airflow. How is everything doing? And right now now this is from the single script. Everything else from just one click. Right now we did it. You won't require it in future. And inside the pod, we trained the model. Model got registered. So you might also see the CPU usage got spiked during the training, but it's a very small model, and that's how the loop is closed. So although the button click is very simple, but it actually means a lot of things. A single airport triggers Kubernetes creating pod, MLflow logs the experiment, model registers the new version, serves the new model, Grafana visualizes the resources. This is the holy grail of MLOps, not because it's fancy, but because it is automated, reproducible, observable, and production grade. This is the same architectural pattern used by companies like Uber, Netflix, Stripe. Just scale down to your laptop, and now you understand it end to end. And next step, uh, try to change the alpha parameter. It's just an assignment of this training, and rebuild the uh, image using Airflow. Trigger the DAG again. Watch how matrices change. What how resource profile changes in Grafana. That feedback loop is what real machine learning engineer looks like. Congratulations, you just learned tools. You didn't just learn tool actually. You build a complete MLOps system.